Hi, welcome back. Last video for chapter 2 with a little bit of chapter 8.1 thrown in. I'm going to talk about density, and then we're going to talk about graphing and using density graphs as an example of our graphing techniques. So first of all, density. You have been taught that density is the ratio of mass for a sample compared to the amount of space that it takes up. So mass divided by volume gives us our density calculation. And as far as the concept goes, there's really two main things that affects the density of a sample. One, the atoms that make up the sample. If they have a lot of protons and a lot of neutrons and electrons compressed into a small area, then they are going to be high density atoms. And high density atoms tend to stack together in liquids and solids in a way that creates high density. But the stacking itself is also important. So again, there's two things that determine density. One, the nature of the atoms. Are they high density atoms? Two, how are they stacking together? And in this diagram, I'm only showing you three of quite a few different ways that these things can stack together. In AP Chemistry, we study this and we call it a unit cell, how the particles stack together, and it's typical of solid and liquid state structure, not gases, because gases, the particles are free to move about however randomly that based upon their kinetic energy. But if we form a solid, we know that the particles have to be right next to each other, locked into place. And in the liquid phase, the particles are next to each other, they're touching, but they're spread out apart enough to allow them to slide over top of each other and pour. So we're just going to look at a solid here. If you stack the atoms together in what's called a simple cube, the problem with that stack is that it creates a lot of space in between each atom, and I'm showing that in red. That's called interstitial space. So if you stack the atoms one on top of each other, then you create all of these grooves where there's empty space. However, in a body-centered cube, if you stack one layer of the atoms in the grooves created by the other two layers, sort of like making an atom sandwich, now you have a more compressed stack and a higher density material. So there are actually low density atoms that create high density materials, and vice versa. But the general rule is the denser the atom, the denser the material that they create. All right, mathematically speaking, we already went over this, so I'm not going to belabor it. When you have a density calculation, anytime you have a numerator over a denominator, that's a conversion factor. That's called a conversion factor. So we have really two techniques we can use to solve the problem. We can either approach the problem from a formula-based perspective, or we can approach the problem using conversion factors. I prefer conversion factors because there are things that you have to use conversion factors for, and it's good to get used to the technique. But since you're trying to get an A, whichever technique works for you is what you should use. So I'm going to approach the problems both ways. All right, so we go to our little slideshow. Hey, I just mentioned this. I like conversion factors. The one thing you can't use is algebraic proportions. So if you're going to use proportions, you have to make them into the form of a density formula and then solve for the variable and then substitute in. Make sure you have your number, unit, and label. So here's a problem. Suppose we have a particular alcohol. We know the density of it. They give you the mass. They want you to predict the volume. So we can approach this one of two ways. Oopsie poopsie. Hang on. All right. We can do a formula-based approach. So we can say, all right, density is mass divided by volume. Now we have to solve for volume. So volume is going to be equal to mass divided by density. And now we can substitute in number, unit, and the label of the chemical. So the number is, the mass is 32.8 grams. We could write alcohol as the label, but we don't know which particular alcohol it is. So I'm just going to abbreviate it ALK. 32.8 grams ALK. And then we're going to put that over the density. So 0.84 grams per milliliter. That's the unit. ALK. Alright, so now we just have to do a little bit of calculation. So we take out our calculator. 32.8 divided by 0.84, and we get 39.04761905. How many sig figs? According to the last video, when you multiply and divide, you choose the entity with the least amount of significant digits, and that's how many you use for your final answer. So we're only going to report the first 2 significant digits. So our answer is 39 milliliters of alcohol. Now, if we're doing this as a conversion factor, start with what they give you. Now, density is a property. It's a ratio of this material. That's not what you're starting with. What you're actually starting with is 32.8 grams of the alcohol. So we're going to write that, 32.8 grams alcohol. We're going to multiply by a fraction, get the grams of alcohol to cancel out, and then we're going to convert that to milliliters of alcohol. Now, the number for that comes from the density ratio. So I'll find density right here, 0.84 grams per milliliter. That means per every 1 milliliter. So if I had 1 milliliter, I would have 0.84 grams. And you still get the same calculation. 32.8 divided by 0.84 comes up to be 39 milliliters of alcohol. Either technique is acceptable. Alright, when you go to graph, and I'm going to use density as an example of a linear plot, here's the rules. If you're doing this on free response or in your lab notebook, dedicate the whole page to the graphing, because there's 2 graphing techniques. One is called linear recursion, and that is introduced to you at the end of pre-calculus, and pre-calculus is not required, so we're not going to do any linear regression. Second is called graphing technique, and in order to get a good sense of what's happening with the slope of your line, you have to make that graph as big as possible. So it would be ridiculous to make the graph as big as a football field, because you would have to tape a lot of pages of paper together. So we're just going to limit it to 1 page, but we want the whole page dedicated to that graph. When you title the graph, it has to be descriptive. That is, if I have you calculate the density of an element, you should write the density of sodium or the density of gold. You shouldn't just write density, because if you write density, that means the density of everything. And different things have different densities, so it's untrue. So we're going to come up with a descriptive title for our graph. And then the X and Y axis, we are going to label them with the units. And we're only going to focus on the first quadrant. And the reason why we're going to focus on the first quadrant only in our X and Y plot is because these are positive values. We're not going to have negative physical entities. You can have a negative direction, but you can't have negative entities. There's no negative mass. There's no negative volume. When you plot the points, you're going to do the same thing as algebra. Plot them the same way as you do in algebra, but I'm going to put a little star next to here. Be careful. Lab data is not an XY chart from algebra. It's not. So be careful. You have to read the data and you have to plot it based upon the relationship. And then finally, we'll talk about how to draw a best fit curve. That's the whole purpose of our graph. And we'll talk about what the slope represents. So let's do a graph involving density. Alright, so suppose we have the following data. We do a lab and we're going to run this trial. Let's do 5 different trials. We do a trial, we calculate the we measure the mass, we measure the volume. And so in trial 1, we find that the mass of our sample is 2.63 grams, and the volume happens to take up 5.31 milliliters. Then, second time we do a different sample. Let's say it's 3 grams, and it comes out to be 5.98 milliliters. Third trial, going to come up with a data point. And then 4th and 5th trial as well. Alright, so there's our data. Now, when we're creating data in our lab book, we like to make columns out of things so that it's easy for us to read the data. But when you make this column, what confuses students is they go back to algebra and they say, oh, this is an XY chart, so mass must be on the X and volume must be on the Y. Well, that's not the case. If our intention is to graph density, density by definition is mass divided by volume. So if we're going to use a linear plot, that density is going to represent the slope of our line. And the slope of the line is actually delta y over delta x. So if the equation is delta y over delta x, that means our y-axis component is the mass and our x-axis component is the volume, regardless of how we set it up in our data table. Okay, so we're going to use that data and we're going to create a graph, and I want that to be a full page, so I'm going to hit copy. Let's scroll down a little. Want a whole page for our graph. Then we're going to paste this data. So I'm going to shrink that data down and put it over there on the side so I can use it. And I'm going to use the rest of the page here and dedicate that to my graph. Alright, so let's say that we find that we are testing samples of nickel. So this is going to be a graph of the density of nickel. Not density, density of nickel. So we're going to put mass on our y-axis, and we're going to put volume on our x-axis, because when we graph the slope of the line, we want it to represent that numerical relationship where density is mass over volume. Okay, so what's our units for mass? It is the gram. What's our units for volume? In this case, it's the milliliter. So now we're going to plot the points like we normally do. Let's set up our axis. We want to stretch this axis. So if mass goes from 1 to 5, we're going to put the 5 up here, and then let's say we do 4, 3, 2, 1, like that. And for volume, our maximum is around 10. So we're going to put that out here, and we'll do 2, 4, 6, 8, and 10. Okay, we can do that. Of course, this is a little sloppy, so I'm going to get rid of the volume, and I'm going to draw it a little bit better down here. And now we're going to plot points just like we do in algebra. So we got 2.63 grams and approximately 5.3, actually should be over here, milliliters. And then we got 3 grams at around 6 milliliters. And we got 1 gram at around 2 milliliters. And then we got 2 grams at 4.8, so a little bit past the 4. And 5 grams at 9.91, so a little bit less than. Let's go here actually. It's hard to tell. I mean, if I zoom in, I can get rid of that. Looks a little bit better. Alright, once we plotted our data points, notice they don't fit exactly on a straight line. Although we know density to be a straight line graph because it's in the formula y over x. Delta y over delta x, the formula for the slope. would be y2 minus y1 over x2 minus x1. So what we're going to do, since we know this is a linear relationship, is we're going to draw something called a best fit curve. Now, the reason why the data is not on a straight line, I started to say and then didn't answer, is because of indeterminate error. Sometimes we measure too high, sometimes we measure too low. If we do a lot of data trials, it will cancel out. Before I draw my best fit line, I'm going to ask myself, is the origin a data point? In this case it is. If we had 0 grams, we would have 0 volume, so I'm going to use the data point to kind of anchor this. And then we're going to draw a line that shows half of the data above the line and half of the data below the line. So I'm going to get out a ruler here and I'm going to try to make an estimate the best I can where some data points are above the line and some data points are below the line. That's not bad. That's not bad. Again, sometimes we estimate too high, sometimes we estimate too low, and this drawing where we're trying to average out that error is called a best fit curve. Now don't tell me it's not curvy. A curve just means an algebraic plot. So the density of nickel, we got our curve. Now sometimes they might ask you to calculate the slope based upon your data. When they ask you to do that, they're not asking you to use, like for y2, y1, they're not asking you to actually use these data points. They're asking you to find 2 points on your straight line and then do y2 minus y1 over x2 minus x1. But the truth of the matter is I only asked that at my AP level, and that's when we get into using a Excel spreadsheet in order to do linear recursion. So I'm not expecting students at this level to do a slope, but you should be able to do it. If you do a density lab, then you have to find the slope, because the idea of the density lab is to determine the density, and the density is that slope. So we're going to write M for slope is equal to density. So in a lab report, I would probably ask you to calculate the slope. I may or may not. I'll ask your recitation and lab instructors if they want me to put it on there. I don't normally put it on there as a calculation because I know you know it from Algebra 1. All right, finally, linear plots versus histograms, and we already talked about Gaussian statistics and standard deviation the last time. And then I'm going to talk about direct and inverse relationships, and we are done. Okay, first of all, difference between a histogram and a linear plot. Linear plot gives you that slope. A histogram, we're looking at frequency versus data. How often did that data occur? So an example of a histogram would be, let's say we have 10 coins, and we want to count for every time we flip 10 coins, the number of heads that we get. And this is the example that I used in the last video. So we're going to set up our graph, and 0 heads, there's no origin on this histogram because 0 heads is actually a possibility. 1 head, 2, 3, 4, 50-50, right? 6, 7, 8, only 1 tails, no tails, so 10 heads. And then we flip the coins, and I'm going to set up my axis over here. 1, 2 occurrences, 3, 4, 5, 6. So again, this is going to be occurrence versus number of heads from that occurrence. So the first time I flip the coins, I get 50-50. So that's 1 occurrence. Next time, I get 4 to 6. Then I get, again, 5 to 5. Then I get 7 to 3. Then I get, 3 to 7. So you keep track of how many times you are getting this occurrence. And if you do enough trials, eventually your data on your histogram is going to look like this. And what does that resemble? Well, if we do a linear plot of it, it resembles our Gaussian curve. So histograms are used to construct Gaussian curve. Last part. They think you remember the difference between a direct linear relationship versus an inverse linear relationship. Okay. In a direct relationship, as quantity A goes up, so does quantity B. Now in biology, we would call A the independent variable and B the dependent variable. But in chemistry, we're verifying stuff. So when we do analysis, it would be inappropriate to say that the mass is a function of the volume change or the volume is a function of the mass change. They work together in concert. So one is not really independent of the other. So very rarely in chemistry do we identify a independent versus a dependent variable. It can be done in certain experiments, but at this level it's not done very often. So if we graph this, we might have A on the y-axis, B on the x-axis, and depending upon the values, we're going to have a positive slope, but the actual slope is dependent upon the values that we're actually graphing. For inverse relationship, again, we're only using the first quadrant. As quantity A goes down, quantity B goes up. So our graph is going to look something like this. Again, the slope and the intercept really depends upon what it is that you're graphing. And that's it. Nice short video. Thank you very much.